And let's build up our notation step by step. I should warn you that, yes, the notation is going to get a little hairy, but there is going to be a value at the end of all of this. At the end of all of this, we're going to have a formal edifice, a structure on which independence crops up essentially for free. Look, and this is a desideratum well worth the candle. So let's begin with a consideration of a compound experiment broken up into two individual chance experiments, two independent trials. The first trial results in a space of possible results. We'll call it Gothic A. And Gothic A is a set of possibilities, which I shall denote A sub j, j running over a finite or possibly a countably infinite range. So, for example, in a coin toss, A1 was heads, in this case a green head, and A2 was a green tail. Right? But now more generally, if you imagine that the first trial involved a throw of a die, then the AJs could be the numbers 1 through 6. The atomic mass function here need not be combinatorial anymore in general. In other words, we can assign atomic probabilities to individual masses for the first trial. To the mass AJ, assign a chance P sub j. Excellent. Color-coded green to keep in mind that this represents things for the first trial. The experiment is not concluded. We're now going to do another chance experiment, a second individual chance experiment, a second trial. Its results are captured in a set, let's call it Gothic B, and Gothic B could be a finite or infinite set. Let's call the elements of Gothic B, B sub k, where k ranges over various finite or infinite ranges. We're going to call it B sub j instead. A rose by any other name would smell as sweet. Your index j or k here just identifies various elements in the set. But it would be nice and wise to keep the indices representing the generic results of the first and second trials separate. So let's use an index j for the first trial, an index k for the second trial. Of course, j and k are generic algebraic variables. We color code this, let's say, by a blue color. So Gothic B and the various elements of Gothic B are the potential results of the second trial. It's a chance-driven experiment, and therefore we want to allocate chances to each of these atoms. To the atom B sub k, suppose we allocate a chance Q sub k. Nothing says that the experiments have to be the same. For example, you could throw a die as a first trial and toss a coin at the second trial. What matters is that they've got a finite or countably infinite range of possibilities, and that for each of those possibilities, you've got an atomic chance. P sub j in the first case, Q sub k in the second. Now we're going to stitch these two together to form a compound experiment. We shall call the resulting sample space a product space for natural reasons, and the resulting probability measure a product measure. The sample space, omega, is now the Cartesian product of Gothic A with Gothic B. What does this mean? The sample points are ordered pairs. A sub j results of the first trial, cobbled together with B sub k resulting from the second trial, j and k ranging over all possible indices in your index sets. And now we naturally have what we call a product space. You're taking a Cartesian product of two trials. What makes things independent is a specification of the probability measure. I'm giving you a discrete setting here, a finite or a countably infinite setting for this compound experiment. It suffices to provide an atomic mass function to every atom a probability. What are the atoms in this game here? The atoms are ordered pairs, first trial, second trial. Suppose the first trial results in the result A sub j, the second trial results in B sub k, then we have an atom A sub j, B k, to which we attach the probability P sub j times Q sub k. This is where the independent trial part of the experiment comes into play. independent trials means that the compound probability mass function is obtained by taking as a product the individual masses. Once you've got this in play, we can now start stitching together events. Okay, now we need a little more notation. Keep in mind the key idea. If you have an event determined solely by the first trial, it should, if we've said our prayers at night and been very good, be independent of an event specified solely in terms of the second trial. We've now set up what the product space is for the compound experiment, a system of pairs, a Cartesian product. And this was the key element, what it meant to have a product measure. This is at heart what we mean by independent trials. The atomic probabilities multiply to give us the atomic probability for the ordered pair. We should now set up events. And again, the key idea is to set up events which depend upon separate trials. An event A, which depends only upon the results of the first trial, and an event B, which depends solely on the results of the second trial. We're going to need some formalism and some notation to carry us through this. What does it mean for an event to determine or to be determined by the first trial? It means that that event is ultimately determined by some subgroup of possible results of the first trial that occur. We identify the locations of that subgroup with, let us say, blackboard J representing a collection of indices representing locations or points in the set of possibilities Gothic A. So blackboard J represents, say, this location, that location, 1, 3, 9, for example. Okay. Likewise, we set up a system of possibilities for the second trial. Blackboard K represents a collection of outcomes, results of trial 2. Again, these collections, J and K, could be finite or even countably infinite. Okay. What does it mean to say that an event A depends only on the first trial? Well, if A occurs whenever the results of the first trial were any of the tagged locations identified by blackboard J, then we will say that A was determined by the first trial. Let's put this in notation. The elements tagged by blackboard J in the first set Gothic A give you a subset of Gothic A. Call that Gothic S, just temporarily as a nonce notation. Gothic S represents a collection, a sub-collection of results of the first trial, which are identified by a particular set of locations, a set of indices, blackboard J. An event A, which is determined by just that set, in a formal sense, depends only on trial 1. What does this mean? Suppose A is an event, a system of pairs, where the first element, A sub j, is one of the tagged elements in Gothic S. The second result, the second element, B sub k, representing the result of the second trial, is completely unfettered, can be anything whatsoever. The first element is constrained to a particular set, the second element is unconstrained. Naturally, we will say A is determined by the first trial. A occurs or not occurring is not dependent upon the second trial. It only depends on what happened in the first trial. Likewise, an event B, which depends only on those results identified or tagged by the blackboard K set of indices for the second trial, and does not depend upon the first trial, is a system of pairs, AJ, BK, where AJ now, the result of the first trial, is completely unfettered, whereas the result, BK, of the second trial, is one of an identified subset of possibilities, which I've identified, let's say, by Gothic T. In a very natural sense, A depends on trial 1, B depends on trial 2. We would anticipate that they are independent. Now, what does independence for pairs of events mean? That we have a rule of products for intersection probabilities. And therefore, we need to construct a third event, the event A intersection B. I'm going to call this a rectangular event because of a graphical reason I'll come to shortly. What does A intersection B mean? A intersection B is now a subset of ordered pairs, A sub j for the first trial, B sub k for the second trial, where A sub j is in the tagged group of the first trial and B sub k is in the tagged group of the second trial. In other words, now the first and second trials are not both unfettered. A sub j has to be in one of an identified subgroup, B sub k has to be in one of an identified subgroup. We'll call such intersections rectangular for simple graphical reasons. If you imagine that the subset of indices blackboard j represents, let's say, the interval shown on the upper right of the screen, and the subset of indices blackboard k represents another interval on your screen, then if you allow the first index to be in blackboard j, the second index to be unfettered, you get a strip. If you allow the second index to be only in blackboard k, the first index to be unfettered, you get another, this time horizontal strip. The intersection of those two give you indices where the first element is in blackboard j and the second element is in blackboard k. In other words, you get visually a rectangle. Okay, now we abstract this principle and call such sets in general rectangular sets. Okay? All this means is that the first element varies freely over some set, the second element varies freely over some other set. And the result is what we call a rectangular set. Of course, what matters now is what are the chances of all of these events, and does a rule of products emerge? Let's pause and take a look at this now. First, we start with the individual chance experiments, and we're allocating mass functions to each of them. P sub j for the first, Q sub k for the second. Naturally enough, the mass functions have to be non-negative, and they have to be properly normalized. All possibilities for the first trial have to add to 1. All possibilities for the second trial have to add to 1. So the pj's add to 1 and the qk's add to 1. Excellent. This is setting the stage. We're now looking at the compound experiment. Now, in the compound experiment, we're looking at ordered pairs, and the mass function allocates probability pj qk to the atom consisting of the ordered pair aj bk. Our first question should be, well, this is a by fiat of definition. We're just writing down what we say, what we claim is going to give us a probability measure. Does it in fact give us a probability measure? Now, if you multiply two non-negative numbers, you're going to get a non-negative number. So positivity is trite. The atomic measure is going to give you non-negative numbers. The question is it properly normalized? And of course, this should be checked, right? This is a sanity check to make sure the foundation is solid. So we want to add up over all possibilities the atomic probabilities, which are of the form pj qk. But if you sum over all j and all k, we can simply separate the sums into a sum over j of pj times a sum over k of qk. Each of the terms in the round brackets is 1 because the individual mass functions for the individual trials are suitably normalized. So you get 1 times 1, or in fact 1. This atomic measure is in fact suitably normalized. It gives rise to a bona fide probability measure. Now let's turn to the events. What can I say about the chance of the event A? Naturally enough, by additivity, we sum over all possibilities for the atoms in A. What are the atoms in A? Well, they are pairs, A, J, B, K, where J ranges over an identified subset of integer indices, blackboard J. K is unfettered, can range over all indices. Again, the sum factors into a product of two sums. Your first term, the round brackets, is a sum over a restricted range for the index J over the identified locations for the first trial over blackboard J. Sum over indices in blackboard J of the probabilities P sub J. The second term in round brackets just sums over all possibilities for Q. But the QKs are properly normalized. They add to 1. The second term vanishes quietly like the snows of yesteryear, leaving you simply just a sum over a restricted range of indices, blackboard J, of the probabilities Pj. Likewise, an entirely analogous argument gets us the probability of the event B. To get this probability, we have to sum over all atomic probabilities for the atoms in B. The atoms in B are pairs A, J, B, K, where J is unfettered, but K now is in a restricted group, a blackboard K set of indices identified ahead of time. The first sum now is 1 because the Pj's are properly normalized, and so we now get an expression for the probability of B as a sum over blackboard K of the probabilities Qk. Very good. And now the million-dollar question. What can I say about the probability of the intersection of A with B? Again, we sum over all possibilities, but now we are looking at ordered pairs where the index J has to lie in the identified subset blackboard J. The index K has to lie in the identified subset blackboard K. We separate the sum again into a product of 2 terms. The first term in round brackets is exactly what we've identified as the probability of A. The second term in round brackets is exactly what we identified as the probability of the event B. And therefore, inevitably, the probability of A intersection B is exactly the probability of A times the probability of B. A rule of products has magically emerged from this notational mess. Of course, you realize that this argument is impeccable however I chose the identified set of indices blackboard J, however I chose that particular subset of Gothic A that triggers the first event, and however I chose the second subset of indices, blackboard K, which gives us a subset of Gothic B. And therefore, we've discovered that any events A and B so constructed, where A is determined by the first trial in the sense that I've outlined here, and B is determined by the second trial again in this sense, any 2 such events are forced to be independent, provided the probability measure is obtained by multiplying independent probabilities. The probability measure is a product measure obtained by multiplying probabilities from independent trials. Here is a wonderful general principle. Notice, the moment I can make this claim, the moment I can identify events like this, the necessity for checking independence goes away. The moment events can be so broken up, we automatically get independence. This is what I mean by the necessity for checking independence is not there anymore. Independence is now transparent in such a setting. Our next step now, of course, is to take what we've done for 2 trials and quickly expand it into many, many trials. And this is what comes up next.